Hello and welcome to the Daily Space for today, September 16th, 2019. I'm your host, Dr. Pamela Gay, and I am here to have technological fail and to put science in your brains. Most Mondays through Fridays, either I or my co-host Annie Wilson will be here to bring you a quick rundown of all that is new in space and astronomy. Now, today's episode is going to be a little bit different than normal because instead of going through a variety of different stories, we're going to do a deep dive into one story. And this is an extremely important story that I think is worth spending the time on. For the past couple of years, we have been reporting off and on about new arising discrepancies in how old we understand our universe to be. And we're starting to get better and better data. And I wanted to explain to you, first of all, how it is that we understand the universe that we live in, and then what those discrepancies are and how it is that we're slowly working to try and understand what it is that we actually see. So I'm going to start by basically going all the way back in time to, well, the beginning of the universe and the more modern understanding that we have of that universe. So originally, we didn't have any way to look out and understand our universe from a scientific perspective when it came to the details like how is the universe expanding or not. And all the way up into the early 1900s, this was actually the domain of natural philosophers. Folks would look out at our universe and look in at what they felt was true and make proclamations like our universe must be static and infinite. And even though the modern religions of the time, for the most part, said that our universe had a singular beginning, when we looked out to imagining our models for space, we were more infinite in what we looked for. But this was problematic. And the problem was best articulated by, and here I need to look at my notes to get the correct dates, by Henrik Olbers in 1823. What he said, and what is now known as Olbers Paradox, is that if our universe were both infinite in age and infinite in size, there'd be no darkness to the sky. Every direction that we looked in, all our observations would end in a star. And given the fullness of time, that starlight would have time to reach us. Now, if our universe were infinite in size, but not in age, then there would be stars that, sure, they're along our line of sight, but their light hasn't had time to get to us. If our universe was infinite in age, but not in size, there'd be directions that we looked along that there were no stars. So the fact that we see darkness in the sky points to our universe being finite in either age or size or even both. Now, while Olber gets all the credit for this, and they name it Olbers Paradox, he wasn't the first person to articulate this observational concern about the nature of our universe. This particular concern was brought up by Thomas Digges and Johannes Kepler, among many others. Those were just the dominant names. And this quandary just sort of stayed at the back of people's minds through the years. And it was in 1917 when Einstein was working on his formulation for the cosmological implications of the theory of general relativity that he relied on that philosophical notion that our universe should be static, that led to him, when he looked at his equations, there's what's called a constant of integration that crops up mathematically. There are certain things that you do in calculus where you're looking at a particular feature, and when you integrate back to figure out what led to that particular feature that you're seeing, you don't know necessarily the starting point. So when you integrate, you add on what's called a constant of integration. And the cosmological constant is really nothing more than that constant of integration, that when Einstein looked at his theories and he ran the numbers, there was an integration step, and he put in a constant, a cosmological constant that he gave a value to that would stop the universe from either expanding or contracting. And in fact, his math, without that constant, defined our universe as being in motion. Now, 1917 was still beginning times for us in our observational way of looking at our universe. And this was a turning point in many ways. So Einstein's paper came out in 1917, but while he was in the process of looking at this, at the same time, we had Vesto Slipher, who was working at Lowell Observatory, taking a myriad of what are called spectrums of galaxy. This is when you look at a galaxy and you use a prism or a grism or a grating or a slit. You use some technique to spread the light of that galaxy out into all of its individual colors. And when you look at this rainbow, you can see dark lines where different atoms have absorbed out the light, and you can see bright lines where atoms that have been specifically excited are emitting excess light. And these patterns of absorption and emission lines are dictated by what are the atoms in galaxies. And mostly galaxies are all made of the same stuff. So when you look at this pattern of light and dark lines superimposed on the rainbow, you can see that those lines will actually shift redward and blueward. And those shifts are representative of the velocity of the galaxy. If the galaxy is moving towards us, all of its light gets shifted blueward as its motion causes the light waves to get compressed. The same way we hear sound waves is getting the same way we hear sound waves getting compressed when an object is moving towards us. Now, if an object's moving away from us, this stretches out the wavelengths of light, making them appear redder than they actually are. Again, the same way we hear the pitch change in a fire truck as it recedes away from us. Now, when Vesto Slipher looked at pretty much all the galaxies he could reach from Lowell Observatory, these were all the galaxies that were in the right part of the sky and were bright enough for him to be able to spread their light out effectively and still see light. Well, if our universe was static, as was expected, you'd expect there to be motions, but randomized motions, where the same number of galaxies were moving towards us as were moving away from us, and there'd be a distribution of motions that could be statistically described as random. But that's not what Slipher saw. What he saw instead was the bulk of the galaxies appear to be moving away from us. Now, what he didn't have was the ability to measure where those galaxies are in space. All he could see was these galaxies seem to be, as a whole, more often moving away from us than towards us, and this doesn't match the present understanding. So this is where Hubble comes into the picture, and his night assistant observer and collaborator on much of this work, Milton Humason. And with Humason at the controls for the telescope, they did a variety of new observations that allowed them to take advantage of a technique that had been developed in 1912 by Henrietta Leavitt, where she had realized that when you look at certain stars, they pulsate in a very systematic way that can be easily observed. And the rate at which they pulsate is directly related to the size and the luminosity of the star. This is, to use another analogy, the same way the sound that comes out of a tin whistle is a direct relation to how much of the tin whistle you allow the sound to come out of. When you push the stopper in all the way, you get one pitch. When you pull it out all the way, you get another pitch. So you get a different period depending on the size of the star, just as you get a different sound depending on the size of the tin whistle. Now, it's actually the same physics, the same harmonics that are occurring in both these kinds of systems, where the harmonic you're allowed directly corresponds to the sound of what's resonating. And with stars, if you know that stars that have this one resonance, this one periodicity, all have the exact same actual amount of light coming off their surface, you can look at the star and say, oh, I know that star is supposed to be this brightness, but it appears to be much fainter. That means it's this distance away. Oh, it appears to be even fainter than that. It must be even greater distance away. And there's simple math to go between how luminous an object actually is and how bright it appears that allows us to calculate the distance to those objects. So Hubble took the Leavitt relationship from Henrietta Leavitt, took Vesto Slipher's velocity measurements as well as his own velocity measurements, and combined these to make a plot of the distance to a galaxy versus how fast it was going. And what he found was the further a galaxy is away from us, the faster it appears to be moving away from us. And this is consistent with an expanding universe. This is something that had actually been predicted by Lemaitre earlier. And this changed how we had to look at the universe, where suddenly, instead of being something static and unchanging, we were looking at something that was expanding. And there were two possibilities at this point. Either our universe had emerged from a single point in time with the entire universe expanding, not out from a single place, but just the entire universe expanding, carried with the initial velocity that set it in motion. Or you have an entire universe that, much like sourdough starter, every bit of that universe is constantly expanding as new stuff comes into it all the time. These two different models, however, have very different observable outcomes. If you have a universe that all once was compressed down to a single point, then you're going to have temperature variations over time. You're going to have, well, a point of beginning when the size of the universe goes to zero. And it was James Peebles, working at Princeton University, who worked out that if we have that expanding out, that Big Bang universe, we should have had a point in time when the entire universe was so hot and so dense that light trying to move through the universe would be unable to go anywhere. The universe was essentially opaque, and atoms and electrons, or I should say atomic nuclei and electrons, were constantly colliding with one another and absorbing and re-emitting light. And to get from that opaque universe to our modern transparent universe, you have to have a moment when atoms form, when those electrons glom onto the atomic nuclei. And in that moment, suddenly light at a very precise temperature is set free to fly through the universe. And no matter where we are in the universe, we should be able to look out and see at a set distance defined by the age of the universe, a wall of light that came from that sphere at that moment of time and then has had time to travel all the way to us. This wall of light is the cosmic microwave background. And it was found in one of perhaps the best possible examples of one man's noise being another man's signal in 1964. Penzias and Wilson were actually trying to define astronomical sources of microwave radiation that would appear as noise in ground-based communications. They were looking at things like, how does Jupiter affect signals? Where are there other sources in the sky? And they were expecting to find discrete places on our sky where there was this microwave signal that would interfere with communications. And they found those points. But then they also found between them, everywhere they looked, this background. And that background they found was what Peebles had predicted. In a great moment of the Nobel Committee acting as it often does in weird and unusual ways, Penzias and Wilson both got the Nobel Prize, and Peebles did not for this particular discovery. But this discovery was what let us know we live in a universe definitively that had a Big Bang and has been evolving out since then. And there's other lines of measurement that go with this as well. The Big Bang theory predicts out a certain amount of heavy material that should have been formed, hydrogen, helium, ratios of lithium and beryllium that all should have come out of the Big Bang. And all of our observations over and over say this understanding is correct. Now, the thing about looking at a universe that has expanded out from a single point is you should be able to work backwards to a point in time when the universe was a single point, and then it expanded until now, and there should be a rate of expansion that we can measure. We call this rate of expansion the Hubble constant. And from the 1960s to the modern day, we've been trying to understand what that Hubble constant is and how the current expansion of our universe interplays with effects like the pull of gravity that want to reverse the expansion of our universe and cause it to collapse down. Now, up until the late 90s, when we imagined our universe, we imagined it as having three different scientifically understood possibilities. One possibility was if our universe had too much mass in it, too high of a density of material. Over the fullness of time, the universe would collapse back in on itself, pulled back together by gravity. If there was a precisely balanced amount of mass, then that mass would slow and slow and slow the expansion of the universe until asymptotically, over the fullness of time, our universe came to a stop. And then the other possibility was that, again, given the fullness of time, gravity wouldn't have an effect and our universe would just keep expanding outwards. And all of this kind of assumed that we're mostly just dealing with two factors, the expansion outwards and the pull of gravity inwards. But then in 1998, when we made the measurements, looking back in time, looking at what is the expansion rate now, what is the expansion rate then, what is the expansion rate even further back in time, what was found was our universe is actually accelerating apart. And well, now we have a new factor that we need to deal with. That cosmological constant that Einstein originally used to stay the motion of our universe now needed to come back into play as that thing that is accelerating our universe apart. Now, we don't know what it is that's accelerating our universe apart because we like to name things and we are bad at naming things. This thing that is expanding our universe has been given the name dark energy. Now, we don't know if it's actually an energy. We have no idea what dark energy is. We just felt the need to name it. I had nothing to do with this name. Now, since 1998, people have been working really hard to try and reconcile, okay, so how is the universe accelerating apart? And what is the cosmological constant that describes our universe's expansion? And what is the mass density of the universe? Trying to get at, well, what is dark energy? And also just trying to answer fundamental questions like, how old is our universe? And when we try and figure out how old is our universe, we're still working from two major concepts. It's just different two concepts. In this case, it's how fast is it expanding and how fast is that acceleration changing? And we've been trying to get at this information and working backwards to the age of the universe, because if you know how fast it's expanding and you know how that expansion is changing, you can math it backwards to figure out how old the universe is. Well, one of the ways that we get at this is we simply measure how far away things are, and we measure how fast they appear to be moving. And while conceptually this is really simple, observationally this is a bear. We can't see those Cepheids that Henrietta Leavitt taught us about in every universe, in every galaxy that we look at. When we look at some galaxies, we are lucky. This is an example of one galaxy where we can see both what are called type 1a supernovae and individual Cepheid variable stars. And using those Cepheids, and by assuming that all type 1a supernova, this is where a white dwarf star suddenly explodes because its mass got too high for it to be stable under the rules of particle physics. So the idea is when all of these white dwarfs explode, and they should be exploding with the same amount of material, they should be giving off the exact same amount of light. And if we measure how bright they appear, we know how far away the galaxies are. And there's a lot of assumptions in this, but it's the best we've got. And using this technique, the best observers in the world have been constantly working to understand how fast is the universe expanding and how is that expansion changing as a function of time, looking at all the galaxies we can look at. And using these measurements, they've gotten most recently to a value, and here I need to look, most recently to a value of 73 kilometers per second per megaparsec of space. And what that means is every 1 megaparsec of space that we have, every single second, that megaparsec gets 73 kilometers bigger. And then the new megaparsec gets 73 kilometers bigger the next second. And that is the current expansion rate of the universe. And that's great. That's a perfectly reasonable number. Now, the problem is we had for a lot of years, you always want to have more than one method for when you say a result. We'd been using as a comparison to that expansion rate derived age of the universe another technique that instead looked at the cosmic microwave background, that wall of light that Penzias and Wilson had been looking at. And looking at this wall of light, specifically with the Planck satellite, we were very precise in saying the universe is 13.82 plus or minus this tiny amount billion years old. And we got to that age by looking at the variation in temperature and density of this map. In this map, the red and blue points, these are places where the universe was a little bit denser, a little bit hotter, places where the universe was a little bit less dense, a little bit cooler. And in these different places, we can measure the size of the variations. We can measure the numbers of each of the different sizes of variations. And we have a predicted set of peaks. We have a prediction in what we should see. And by knowing how big those peaks physically should have been, and by measuring how big they appear on the sky. So this is sort of like when you look at a school bus and you know the school bus takes up your entire field of view, you're about to walk into it. The school bus is this itty bitty little thing on the horizon, you know it's very far away. Well, that same idea, looking at the cosmic microwave background, we were able to take the angular size of these peaks and valleys, these color distributions, these temperature variations. And we're able to use those in our measurements of the mass density of the universe and derive an age for the universe. And from that, derive an expansion rate. And all of these numbers matched as long as the error bars were big enough. And the value that we got from this technique was, looking at my notes again, this technique got us 67 kilometers per second per megaparsec of space. 68 if you round up. 68 and 73 aren't the same number. But when the error bars were large enough, they still overlapped and we were fine. But the error bars don't overlap anymore. They don't overlap so much that it's a 9 sigma error. It's a 9% difference between the values that have an error of only a couple of percent. So this tells us there's something fundamentally wrong in either our understanding of the physics related to the cosmic microwave background radiation or our ability to measure the distances to things. So this is two techniques. What we need is a third. And this third technique is the reason I'm bringing all of this to you today. This third technique that is currently being used is to look at how large things appear when viewed over different distance models. Now, things are about to get trickstery, not that they weren't already. So large amounts of mass has the ability to actually bend the path of light. If my microphone was a massive galaxy and you were observing me off in the distance, what you would see is, because the microphone is directly in front of my face, light that was trying to go off to the sides of my room would get gravitationally bent towards the camera, and you might see multiple images of me. Well, that would be thoroughly creepy, and luckily is not something that can happen because that size scale of gravitational lensing is not a thing. But what does happen is massive galaxies are capable of bending the light from extremely distant bright galaxies called quasars. And these extremely bright galaxies, their light, as it gets bent around the nearer massive galaxy, might get bent in multiple ways where we see multiple images of that background object. And that's what these two images are. There is a central massive galaxy in each of these systems. And surrounding that, labeled things like A, B, C, D, are a variety of repeating images of the exact same background object. Now, each of these different images that are getting repeated has traveled a different distance through space. Some of those light rays, to go back to our microphone as a massive galaxy example, some of those light rays might have gone out a large distance before hanging a left to come in. Some might have done a glancing blow before coming in. And by working through the geometry of each of these different light paths, if the universe wasn't expanding, we'd be able to simply say, aha, this light path is indicative of this particular triangle. This is indicative of this particular triangle. And the geometry is not all that difficult. Now, where it gets trickstery is because space is expanding as the light is traveling. We, first of all, are seeing the galaxy at a variety of slightly different times, which gets really cool with things that are varying in time in the background. The second thing is we are seeing paths that get stretched out as that universe expands. So any slight differences in path length are only going to get magnified as the universe changes in size. And this particular technique is independent of all the other physics. It doesn't worry about standard candles the same way. We're simply looking at how big do those background galaxies appear, the angular size element of them. And by assuming that something varies in size in a systematic way depending on the distance the light has traveled, they're able to work out what the expansion rate of the universe must be for all of these different various versions of the background galaxy to appear the way they do. And since they've done this now with two different gravitational lenses, they're able to repeat their experiment essentially. And from both these sets of images, they're getting a single expansion rate for the universe. It still has fairly large error bars, but that single value is 82 kilometers per second per megaparsec. And this technique is consistent with its 10% error bars with the 73 kilometer per second measurements that were getting made by looking at supernova results. So this is pointing to, once again, our observational results, our results of looking at the universe and measuring how fast things seem to be receding, are all leading us to the same rough age of our universe. And the thing is, this rough age is younger than what the Planck satellite and its cosmic microwave background results had led us to believe. by looking at the gravitational lenses, by looking at the supernovae, by putting all of these pieces together, we're getting at a younger universe. And we're getting at an idea that the physics of our expanding universe is even weirder somehow than what we had thought. And this is the kind of problem that we love as scientists. There's nothing straightforward about it. It's going to require a leap of creativity, of ingenuity, potentially even of technology to try and understand what's going on. And this is stuff that is going on right now with people working madly to pioneer how we find the answer. And this gravitational wave solution is just one of the creative solutions that's going to be found. Now, we don't know where all of this is going to lead eventually. For all we know, we're going to find that there's some standard third issue that we never even considered that is causing all of these results to be wrong. We don't know. But this right now is perhaps the most interesting and exciting area of research in all of astronomy and planetary science. The only thing that comes close is the pursuit of life on other worlds. And these are the fundamental questions that we all ask when we're little kids. Where did we come from? What is the fate of all of it? Is there life out there? Well, we don't know any of these answers. And this goes back to show you that scientists really are the 5-year-olds who never really grew up. They just grew a whole bunch of university degrees and are taking that curiosity and continuing to see where it can take us. And we don't know where this story is going to end. But it's looking like it's going to end in a universe that is younger than we thought, but luckily still older than the stars. As long as the universe stays older than the stars, I think we're fine. So that's what I had prepared to talk to you about today. And I know that that was one almighty long monologue. And I'm now pulling up the questions. If you haven't typed your questions in already, please go ahead and type them in. And while you type them in, I'm going to remind you once again that this is the Daily Space. And most Mondays through Fridays, we bring you a fast-paced roundup of all that is new in space and astronomy. And clearly, occasionally, we do a deep dive into a single topic. We are also here on Sundays with Annie Wilson's Sunday Science Hour. And in between, we bring you launches, landings, and other space-related events live as they happen. So if you haven't already, give us a follow. Follows are free, and you'll be notified every time we go live with breaking news about this universe we all share. We are a production of the Planetary Science Institute, which is a 501c3 nonprofit. This means that your bits, your subs, your donations, your patronage over on patreon.com/CosmoQuestX, all of that adds up to keep us going and is tax deductible for you wherever the law allows. This month is September, and those subs are discounted for you, but we still get the same reward that we need to pay our bills. So if you could give us a sub, we'd really appreciate it. And that's all I've got. That's all I've got. So I'm going to go ahead and scroll around and see what questions I can find. I see lots of comments on how I was muted at the very beginning. Yes. I don't know why DPI is discussing mushrooms and snakes, and all I can think is Hunter S. Thompson. Sorry about the mic. So what happened on the mic is I had adjusted the volume level so that you wouldn't get completely blasted by a promo video, and somewhere in the process, I broke everything. Yeah. Thank you, Susie, for texting. Yeah, it's Monday. It's Monday. Sorry about that. Kevlar's 9-year-old Labrador thinks she's a puppy. That is exactly how Labradors are indeed. Okay. Thank you for the bits, Planetary Pan. I didn't mean to be muted for so long. I'm so sorry. Sigh. Sigh. I'm sorry. Okay. Looking for questions. Larry, thank you for your comment that it was a beautiful deep dive today. Thank you so much. There are like no questions. You all just like sat there silently while I monologued about the Hubble constant. That is awesome. I kept you completely captive. So DPI 209, what do you want Bang SSH to be an abbreviation for? Because to me, it looks like you're trying to secure shell somewhere. Oh, Sunday Science Hour. That works. Yes, we do need a command for that. Yes, we do need a mod for that. Not a mod, a bot chat thing for that. So Susie is asking, will there be any streaming from DPS this week? I haven't seen any notifications yet. I need to dig in a little bit further. I will admit that it was a slow Monday morning for me due to taking too many allergy meds last night. So I'm still starting my day. Looking to see what else is here. So Astro YYZ comments, thank you for researching so much for this topic. The New Age of the Universe paper, can you post? Yes, all of our show notes will be going live later today over on dailyspace.org. And I will be working to put together a podcast edition of this, although I have to say that the slightly more rambling version that you got live here on Twitch might be a slightly better version this time. But yeah, I will link to everything. Looking to see what else is in here. Hanny had a couple. I totally missed Hanny's questions. What color is Hanny today? Hanny is dark green. The universe would do great at that carnival game where the guy has to guess your age. I agree, but not a question. It is a good comment, though. I wonder if there's a section of chat that my iPad decided to eat. Yeah, I'm going to need a third cup of coffee, Susie. Totally going to need a third cup of coffee. Hello, Brillium90. Welcome to our channel. We do a most Mondays through Fridays rundown of space and astronomy news. And I just finished doing a deep dive into the expansion rate of the universe. I seem to have caught up. Okay, so Hanny is asking, is there a reason some stars are variable, or do all stars do it and some do it very visibly? So at the smallest level, all stars have various things going on at our surface, whether it be large-scale oscillations, sound waves moving through the atmosphere. But the big pulsations that we really pay attention to are ones that occur in a way that is a driven oscillation. So with pulsating variable stars, Cepheids, Aurolaris, or many other kinds, what we're seeing is the pull of gravity as it pulls the star down, increases the temperature of the star as the star gets smaller. And this increase in temperature changes the amount of light that's being given off. And normally, if a star were to radically change in temperature for some reason, change in in radius for some reason, it would bump up to a new size or bump down to a new size where the light pressure pushing outwards and gravity pushing inwards were stable to one another. This is called hydrostatic equilibrium. In some cases, however, as the star contracts down, trying to find a new equilibrium point, the light that is trying to push out, instead of pushing out is absorbed into the outer atoms in the atmosphere, and that energy essentially gets stored for later. And then when the star does collapse down too far, because they always go too far, when they start to expand back out, that start to expand back out also triggers that light that was stored up, that energy that was stored up in the atmosphere, to also be released, giving it an extra push outwards, pushing it past its stable point. And so this essentially drives the oscillation. There's a specific band through what we call the color magnitude diagram. It's a plot of how bright stars appear to be and what temperature they are. And this instability strip, it's actually called the instability strip, is where we find all of these pulsating variables that have this particular mechanism that drives their oscillations over long periods of time. Now, the stars do evolve, they change in color, they change in density, and all of these changes will lead them to leave this instability strip. So while most stars at one point or another in their evolution will pass through this strip, it's just a temporary phase in their identity. And our own sun probably won't go through this because it doesn't have quite the right temperature. It won't be an RLRE or a Cepheid, rather, because it doesn't have the right combination of metallicity and mass. But this is just a fact of evolution in stars. It's a pretty cool one. This is where we start to get into my particular area of research. And my iPad's battery appears to have died. Nope, it just was determined not to come back on. Okay, I'm looking to see what other questions we have in there. So Arinstra asks, how far past the cosmic microwave background are we sure about the universe's expansion? So it's more a matter of how close to the CMB can we get in measuring the expansion. There's this swath of universe that we kind of need the James Webb Space Telescope for, if it ever launches. And I'm kind of at the pessimistic point of if. So with the James Webb Space Telescope, we'll be able to see fainter objects. We'll be able to see redder objects than what we can see from the surface of the Earth. And so where we're limited on the planet is we can only see type 1a supernovae to a certain point before their light is too red to readily access from the planet, and they're too far away to easily see from the surface of the planet with the telescopes we have today. I don't know exactly how far away we can currently get. I want to say it's redshift-ish of 6, several billion light years away, but I don't know the exact numbers and would have to look them up. I'll try and look that up to put into the podcast version of the show. Hey, fellow hoodlum. Welcome. Yeah, JWST definitely should be the telescope which shall not be named. So this is actually research that kind of touches on a whole lot of the stuff that I've done for my own personal research. I started off my career working on variable stars, but in graduate school was recommended to switch out to working more directly on galaxies rather than on the stars and galaxies, because it was deemed that there just wasn't enough funding in pulsating variable stars. So I did my PhD work on the evolution of galaxies at moderate redshifts. Since then, I've gone to work purely on computational problems, but this hits on all the kinds of stuff that I had to learn while working on my various undergraduate thesis, master's thesis, PhD dissertation. I'm quite glad I didn't have to do calculations of the expansion of the universe that considered cosmological constants. That would have made me cry. Larry is saying, I'm confident that if we make it the next few billion years, we will take the helium from the sun to make it last longer. Not completely convinced that's a thing. Hello, Commander Unifex. We've been seeing you around here more and more. Your time zones, you are working very weird hours, my friend. Yeah, that's all I've got. That's all I've got for today. Do you have any more questions? Because if not, I'm going to go continue writing up notes and record this for the podcast edition. How would taking helium from the sun help? I'm tired. Planetary Pan. So if you're able to remove the helium from the core of the sun and replace it with hydrogen, the key is you have to then replace it with hydrogen. The helium eventually takes the place of the hydrogen and causes our star to no longer be a main sequence star, which is a bad thing. If you could pull out the helium and replace it with hydrogen, our sun would stay a main sequence star longer. Don't think that's something that's going to happen. Thank you for the follow, Burrito Freak. I now think I'm going to have burritos for lunch. Yeah, it's a futurism kind of technology that I think is really just destined to stay in sci-fi, which is a perfectly reasonable place for ideas like that to be. But then I'm more on the pessimistic side of many of these kinds of questions. Oh, Larry's getting pizza. You're lucky. I'm going to settle for frozen burritos. Nuked. I'm not going to eat them frozen. So I think I'm going to call it a stop for now. As always, this is the Daily Space. We come to you most Mondays through Fridays right here on twitch.tv/CosmoQuestX. If you ever miss an episode, you can always catch them over archived on YouTube/C/CosmoQuest. No X. It's the one place that we set up so long ago it doesn't have an X. Beyond that, we have also come out with a new podcast edition. You can subscribe to us on iTunes, we're on Google Play, I think. I haven't been able to find the feed, but I don't have an Android device. We have all the links over on dailyspace.org. Please, if you have a podcatching device, go ahead, give us a subscribe. It will really help us in the search engine results and help us reach new audiences. You never know whose life you're going to improve by helping them get a little bit more science into their day. We are supported by you. It is your donations, your bits, your subs, your patronage over on patreon.com/CosmoQuestX. All of those things allows us to pay our staff a living wage. And for that, we are so very grateful. So thank you for allowing us to be here. And if you can't support us financially, that's okay. We get that. Again, share the word, help people find us, and let's get science into more brains than ever before. I am now going to awkwardly realize I have absolutely not set up any of the windows I need to roll the credits because I had that kind of a day. So I'm going to switch screens, dash across the room, start the credits, find someone to raid, go nuke a burrito, record a podcast, and I will be back tomorrow, if not sooner. You never know when I'm going to crop up to do some programming. There is more Bennu mapping to come. Later today, I will be releasing, and this is why I say there may be a coding stream coming. Later today, I'm going to be releasing back into the wilds all of the images that 15 different people opened up on their screen and went, no, I am not mapping that image. Clicked image done to get a new image. So it's okay. We've all been there. We've all been there. But we need those images mapped. So I'm going to be going through and trying to find all those times that someone marked an image and didn't actually mark the image, and re-releasing those images to actually get marked. So that's coming later today. For now, I'm going to get this podcast put together, and I will see you all on the other side. Annie started the credits. Thank you, Annie. So wherever you are in the world, have a fabulous morning, evening, or afternoon. and I'll see you on the other side. Bye-bye.